All right, good afternoon, everybody. Let's get started. So just a quick reminder that our quiz 2 is coming up next week. If you have a conflict with, oh, sorry, thank you. Can you hear me now? Good. All right. So I just wanted to remind everyone that quiz 2 is coming up next Thursday, and if you have a conflict with another exam or something like that, please do get in touch with us through Piazza as soon as possible so we can schedule you for the makeup. Okay. So we basically finished our discussion of how we build our processor, and today we're going to shift gears and start talking about the memory hierarchy. And as was mentioned last time, the memory plays just as crucial of a role in the performance of the overall system as the processor does. And so we want to understand, you know, what do we need to do in order to get good performance out of our memory systems. And so we have a number of different memory technologies at our disposal, and the question is, you know, what's the best way of using them? And so if you look at this table over here, you see that as I go down the table, my latency gets worse and worse and worse as I go to the different technologies. My capacity, however, is able to support much, much larger and larger memory systems. And my cost goes down also as I go down this table. So what this is showing us is really that the different technologies have lots of different trade-offs, and because of that, we use different technologies for different purposes. And so we've already seen that our registers are very fast. So that's the fastest type of storage element that we have. And because of that, you know, anything that we're trying to do very quickly, like inside our processor data path, we want to do with registers. But then we said, well, we can't keep everything in our registers, and so some of our information has to go in main memory. And so main memory is built of actually two technologies, SRAM and DRAM, which stand for static random access memory and dynamic random access memory. And you'll see that already we're, you know, an order of magnitude slower than the registers. However, the capacity that we're able to support with SRAMs is on the order of kilobytes to megabytes, and with DRAM, which is what most of our main memory is made of, we can actually support gigabytes. So now we're starting to talk about significantly, you know, large capacity that we can actually do a lot of work with. And then we have our third category, which is, you know, even though until now we've kind of talked about main memory being humongous and large enough to hold all of our storage needs, in reality, we store so much nowadays that you need more than main memory. And so what we have is flash drives or hard disks in order to store the things that we don't want to lose, but we aren't necessarily accessing at the moment. And so in today's lecture, we're going to focus on the green box, and in a couple lectures, we're going to talk about how do we deal with interacting with this secondary storage or I/O subsystem, and we'll learn about that as well. All right, so for our memory hierarchy, so we said that we have SRAM and DRAM, and but if we look, you know, at this table, we kind of see that there's basically a fundamental limit here. Either I can have, you know, a large capacity but be slow, or I can have some small amount of memory and be fast. And of course, ideally, I want the best of both worlds. So today we're going to be looking at how can we use our memory so that we can actually try to achieve the best of both worlds, so that it seems like we've got a very large memory that's also fast. All right. So let's consider some alternatives of how we can use this memory hierarchy in our system. So here I've shown you a CPU and three different levels or sizes of memory. So we start with the smallest SRAM, which is a 10 kilobyte SRAM. We then have a 10 megabyte SRAM, and then we have our large main memory, which is our 10 gigabyte DRAM. Now, in this implementation, the idea is that the hierarchy of the memory is exposed, meaning that the CPU or the programmer know about the exact setup of our memory and what's available to us. And it's the programmer's responsibility to decide which pieces of data should live in which memory. And so basically, if the programmer knows that there's a particular piece of data that's going to be used frequently, then they would choose to put it in the smallest and fastest SRAM, whereas something that's not used as frequently can go and live in this DRAM. So you can already imagine that, you know, telling the programmers that it's your responsibility to figure out which memory to use for each variable can be kind of difficult. In addition, there's essentially a couple implications that come from this exposed memory hierarchy. The first is that, well, it's one or the other. So either you have to change your instruction set architecture in order to provide instructions that allow the programmer to say, okay, this piece of data should be loaded into the fast SRAM, but this piece of data should be, sorry, not loaded, stored. This piece of data should come, you know, from my medium-sized SRAM. And so if you recall, we learned that, you know, having to change the instruction set architecture is not something that we want to get into. In general, we want to, instruction set architectures should live for a very long time, and so this already is a sign that this might not be the way to go. An alternative to changing our instruction set architecture is to say, well, you know what, I'm not going to actually provide different instructions for accessing the different memory. Instead, I'm just going to say that different portions of my address space refer to different memories, right? So from address 0 to 10,000, whatever, it might be the fastest SRAM, and then the next section of memory would be the next size SRAM, and so on. And so that's at least good from the perspective of not needing to change your instruction set architecture. But now what happens if, you know, I want to add more SRAM to my system? How would I deal with that? What would have to happen in order to support that additional SRAM? I'd have to rewrite all of my programs, okay? So clearly, this is not very feasible, and as a result, it's not really useful in practice. So instead, what we're going to focus on today, which is what is actually used, is this implicit memory hierarchy. And the way this works is, once again, we use the same set of growing memory sizes, except that now, as far as the CPU is concerned, it thinks that there's just a single memory. It sees a single address space, and it can't tell which pieces of data live in which memory, okay? So it makes a load or store request, and that just goes out to the memory as a whole. And it's the memory's responsibility to figure out, well, which pieces of data should live in the faster memory and which should live in the slower, depending on the access patterns of the data. So in this model, suppose that I want to access, you know, an address X. The way that I would do this is that my system would first go and check the fastest, smallest SRAM to see if that address X is stored in it. If it is, then it returns the data very quickly. If it's not, then what it's going to do is it's going to go on to the next one. And it's going to say, okay, is my data in this SRAM? If not, then once again, if it is, it'll return the data a little more slowly than the first one, but still faster than going to main memory. And finally, if it's not in either one, then it'll go to main memory, and there it'll be able to find the data. So what this shows you is that first of all, the processor is going to have to be able to handle different latencies from the memory. And we already know how to do that, right? Our multi-cycle processor can already handle memory responses that are at different rates. So that's great. Whoops, didn't mean to go that far. But what we really care about is that what the CPU effectively sees with this implicit memory hierarchy is it appears to the CPU like it has a large and fast memory, which is exactly what we were trying to achieve, okay? And so we call these different levels of, these intermediate levels cache, and we can have multiple levels of the cache. So here we call them a level 1 cache, a level 2 cache, you can have level 3, and so on. And then eventually we get to our main memory. The caches are implemented using SRAM technology because we want them to be as fast as possible, and the main memory is implemented using DRAM. Okay, so now let's start talking about, well, why is it that the caches work? Why are we able to use this hierarchical memory and actually make it seem like we have both a large and fast memory, rather than, most of the time it taking a long time? And the reason that this is the case is because of two properties of memory accesses. So the first is what we call temporal locality. So temporal locality says that if I'm accessing a particular piece of data right now, then it's very likely that I'm going to access it again in the near future, okay? So think about that for a minute, and in a second we'll see some examples of this. The second property is what we call spatial locality, and this says if I'm accessing a particular location in memory, then I'm very likely to access nearby locations in memory in the near future, right? And that one's pretty easy to see, right? Like if we think about our programs, typically we are accessing instructions sequentially, right? So if I'm accessing instruction A, I'm very likely to access the instruction that immediately follows it. All right, so let's see how these properties actually help our caches. So if we look at the different types of memory access patterns that we have, we've talked about accessing instructions from memory, we've talked about accessing data from memory, and we've also talked about using the stack for our temporary storage of things that don't necessarily fit into our registers. So let's take a look at some usage patterns of those three different types of accesses. So we're going to start with the code, and this is just an example of over time what your access patterns might look like. So who can tell me what, this sequence of instructions that then I see again here and here might correspond to in my program? Yep. A loop, exactly. And what we see here is that I have both spatial locality and temporal locality coming into play. So if we look at the fact that my loop is more than one instruction, I'm fetching and executing a number of instructions that are sequentially next to each other. And I see that in this first execution of the loop. But then I also have temporal locality because the loop gets repeated. And so the instructions that I executed previously are being executed again. Okay? Does everyone understand the difference between spatial and temporal locality? Yes?
So temporal locality is just like a pattern?
No, temporal just means, it refers to the fact that you're likely to, if you're accessing something now, you're likely to access the same thing again in the near future. Okay? And so we see right here how that applies for instructions, and we're going to see in a second how that applies for the stack and for our memory as well, and for our data fetches as well. All right, so here's what your stack accesses might look like. And so if we take a look at this, what I see here is, first I'm in some region, of memory, and this could correspond, to a particular stack frame during the execution of a procedure. And so, here I've got these local variable accesses where I'm accessing something within a single stack frame. And then when I see this jump over here, that's basically a procedure call. And so every time I have this jump here, or here, or here, I'm adding another stack frame onto my stack. Okay, but so what do we see though? We see that while you're within the same stack frame, I have mostly temporal locality because I'm accessing the same elements multiple times. And then I also have spatial locality because I access the elements that are nearby in my stack. Okay? And finally, if we take a look at our data, we see essentially the same kind of pattern repeating itself. Okay, so what do I have here? Here, again, I've got a bunch of sequential accesses, but in this case, this is data and not instructions. So who can tell me what that corresponds to? Or might correspond to? When do I access a number of data elements that are located sequentially, next to each other in memory? Yep. An array, exactly. Okay, so here, what I might be doing is I'm accessing different elements of an array. And over here, maybe I'm copying one array to another array. Okay, so we see that these patterns repeat themselves over and over again, regardless of what type of memory operation that we're doing. All right, so we have temporal and spatial locality present, and so now we want to see, how much can these caches actually help us? So what's the idea? The idea is that we're going to put these things that we're going to access, we're expecting to access again in the near future, into our cache, and that means that whenever we're looking for those addresses, we're going to be able to get them from our cache, and so the response time for memory is going to be very fast. And if we can make it be the case that more often than not we're able to find what we're looking for in our cache, then it's going to appear to the CPU like most of the time the responses are coming quickly, even though it's got a very large address space available to it. So let's take a little bit of a closer look. And so now let's imagine that I have just a single cache sitting between my CPU and my main memory. So what's going to happen when my CPU wants to access a particular location in memory is it's going to send the address that it wants to access first to the cache. Okay? Now there's two possibilities. Either I find it in the cache or I don't. If I find it in the cache, we call this a cache hit, and then we immediately return the data that's associated with that address back to the CPU, and we're able to do it quickly. If I don't find it in my cache, then that's called a cache miss, and then what we do is we pass that address onto the main memory, and we get the response from main memory instead, and the data that comes back from main memory is sent back all the way to the CPU, and in addition, it's sent back to this cache, and now the cache is going to actually store this element that I just accessed, which it previously didn't have in the cache. So that if in the near future I try to access this element again, next time I'm going to get a hit in my cache. Okay? Any questions about that? Great. So, as we mentioned, our processor needs to be able to deal with the fact that sometimes we're going to have hits, sometimes we're going to not, and so the response rate is going to be different. All right, so now let's talk about some cache metrics. All right, so every time we perform a memory access, we either get a hit or a miss. And so we talk about hit ratios and miss ratios, where the hit ratio is the number of hits divided over the total number of memory accesses, which is your hits plus your misses. And your miss ratio is just the reverse, which is the misses over the total number of memory accesses. And because these are just inverses of each other, the hit rate is equal to 1 minus the miss rate, and the miss rate is equal to 1 minus the hit rate. Okay, and what these hit rates and miss rates allow us to define is an average memory access time. Okay, what we're interested in is, on average, how long is it taking us to access our memory? And so what is the average memory access time? Well, if we were able to find the piece of data that we're looking for in our cache, then all we pay in time is the hit time. Okay, so every time we have a hit, we pay hit time. If we have a miss, then we pay both the hit time, which is the time that it first took us to look for it in our cache, and then we also pay the time that it takes us to go to main memory. And so we add miss penalty, which is the amount of time it takes to go to main memory, times this miss ratio, which is how often we're missing and not finding the data we're looking for in our cache. And so for the rest of the lecture, what we're going to constantly be focusing on is, what things do we want to consider when designing our caches so that we reduce our overall average memory access time. So let's first take a look at an example to just get a sense for, are these caches really going to help us at all? And so we have the same picture that we were looking at before, and now let's assign, some numbers to it. And so let's say that my cache, takes 4 clock cycles to respond, whereas my main memory takes 100 clock cycles to respond. Okay, and these are reasonable comparisons in terms of the way that the technologies actually behave. So what does this mean? Without my cache, my system is always taking 100 cycles to respond. So the average memory access time without the cache is 100. What about with the cache? So my latency with the cache is 4 cycles, when I have a hit, and it's 104 cycles when I have a miss. Okay? And so the first question I might want to ask myself is, well, how high does my hit rate have to be just to break even, to get to the point where adding this cache to my system isn't making my performance any worse? And you can basically plug in the numbers here. You have 100, which is the average memory access time of just the memory, and then we have the average memory access time of the memory plus the cache, and that results in a hit rate of 4%. So as you can imagine, that's really quite low, and it's very easy for us to get a hit rate of at least 4%. So already we see that it's going to be very easy for us to do at least as well with the introduction of the cache as we did without it. Okay? But actually, we can do even a lot better than that, right? So if we take a look at what our average memory access time is going to look like for different hit rates, we see here that, if the hit rate is, say, 50%, we're able to almost halve the amount of time that it takes us on average to access memory, from 100 to 54 cycles. Okay? And if we're able to get to as high as, 99%, then our average memory access time is as low as 5, which is almost, the speed of the cache. So it looks as if I'm constantly getting my response from my cache. Okay? Well, so then you might ask yourself, well, can we actually achieve such high hit ratios? And it actually turns out that we can. So for the first chunk of that, let's say about 80%, getting to an 80% hit ratio, just having hardware of that implements a cache will basically get you there. And so we're already, by introducing this new piece of hardware, our cache, able to increase our performance significantly. And in order to get all the way as high as 99, that might take a little bit more effort, where you actually have to think about, when you're designing your programs, how to write them so that they utilize the cache as well as possible. But assuming that you do that, we can even get as high as 99%. Okay? So the caches are really going to help us, and assuming we can have a high hit rate, then it's going to dramatically improve our AMAT. Okay, so we see now why caches help. And now let's start to understand what they actually look like and how we reference them. Okay? So here I've started to blow up a little bit the insides of the cache to see what's actually in there, right? So we've got our CPU, we have our cache in the middle, and we have our main memory. Okay, so the first thing to notice is that in our cache, not only are we storing the data associated with a particular address, but we're also storing information about the address itself. Why do I need to do that? So if you recall, if I have a big main memory, then I just have data here, right? So this would be 0, let's say 579, and I just use my address in order to index into this memory, right? But in the case of my cache is much smaller. So I'm not able to store every single address like my main memory is in my cache. And so I have to have information about, well, which location is it that I actually brought into my cache? And so I will say, you know, oh, I brought address A, and here's its value, and I brought address B, and here's its value. Okay? Make sense? All right, so now let's see how we go about actually trying to do a memory reference. So suppose I'm trying to access address X from memory. Two things can happen. Either I have a hit or I have a miss. If I have a hit, what that means is that one of these tags, which corresponds to the address that that line in my cache is holding the data for, matches the address that I'm looking for. So in other words, if X is equal to one of these, we call these tags, then that means that my data is in my cache, and what I'm going to return to the CPU is the data field of that line. Okay, and so I'm going to return data of that line I where I found the tag match. Now what about if I have a miss? So if I have a miss, that means that none of my tags match this address X, which I wanted to access. So what does this mean? This means that X is not actually in my cache, so I have to go and fetch it from memory. So when I go and fetch from memory, there's a number of things I need to do. The first thing is I need to actually read that location memory of address X from main memory. I need to return the value of memory of X to the CPU. And in addition, remember that I want to bring that value into my cache so that if I was to access it again, next time I would get a hit. Okay, so how do I do that? I need to pick a line in my cache for where I'm going to put this piece of data. So what that also means is I'll have to take something out of my cache because I'm limited in size, and I'll put this new thing in my cache, and then next time if it's accessed again, I'll get a hit. And so in order to put it into my cache, I first have to select a line where I'm going to put this piece of data that I just brought from memory. And once I select that line, let's call it line K, I'm going to update both the tag to say this corresponds to address X and the data to be the memory that came from address X. Okay? Any questions about that? Great. Okay, so this leads us to a question of, well, how do I go about searching my cache, right? If I have to sequentially check every single tag to see if it matches the tag that I'm looking for, you can imagine that that's going to be kind of slow, right? So we're going to have to think about how can I avoid having to check every single tag sequentially. So the first way that we think about doing this is with what's called a direct mapped cache. Okay? So what is a direct mapped cache? In a direct mapped cache, every word or every address maps to a single line in my cache. So how does that work? I basically take my 32-bit address and I divide it up into different pieces. So suppose, I have here a cache that has W lines, or in this example, I have 8 lines. In order to index 8 lines, I need 3 bits to select one of those lines. And so I'm going to use 3 bits of my address to say which one of the lines in my cache is the one where this address is going to be stored in my cache. All right? And so if I look at the details of how this address actually gets split up, the bottom 2 bits are always 0, 0. Why are they always 0, 0? Anybody? Our addresses, yeah?
Addresses are always multiple to 4.
Yeah, because our addresses are in bytes, but we're accessing words from memory, okay? So the bottom 2 bits are always going to be 0. So then we take the next 3 bits, and these are our index bits. And so these 3 bits are used in order to select which one of the cache lines I'm supposed to access. And then all of the remaining bits are what I need to compare to this tag field to see whether or not I have the correct piece of data that I'm looking for. Okay? So in this particular example, I've already used up 5 of my 32 bits, and so I have 27 bits left, which I'm going to compare to the 27-bit tag in my cache. And so what's going to happen? I'm going to say, are these 27 bits equal to the 27 bits that are stored in that line that's at this index? And if so, then if I also have this valid bit being a 1 and I got a tag match, then I consider this to be a cache hit. So let's talk about this for a second. So we introduced one new concept, which is this valid bit. Okay, so until now, we talked about having a tag, and we talked about having, you know, our data that we're trying to store. So it turns out that we also need to have a valid bit for each line of our cache, because when we first bring up our computer, everything that's in the cache is garbage, okay? So we want to be able to say all the valid bits are 0. And only after I've started to bring things in from my main memory, as I bring them in, then I set the valid bit to 1. Okay? So in order to actually get a hit in my cache, not only do I have to get a match of my tag, but I also have to have the valid bit be 1. Okay? Any questions about that? So let's work through an example. So here we have a 64-line direct mapped cache. And so that means we're going to have 6 index bits, okay? And let's suppose that the address that I'm trying to read from is 0x400C, and I'm going to expand that into binary so that we can look at the different bits, okay? So what did we say? We said that my bottom 2 bits are always 00 to do the word alignment. The next 6 bits are my index, which in this example is equal to the value 3. And then the rest of the bits are my tag, which in this case is 0x40. Okay? So what am I going to do? It's first thing is I look at this index. So the index says index 3, which tells me that I'm looking at the line whose index is 3 in my cache. And now I'm going to compare the tag that's stored in that line with the tag that is the address I'm actually trying to fetch from. And in this case, do they match? Easy question? Yes. Okay, so I'm looking for tag 0x40. The tag in my cache is 0x40, and my valid bit is a 1, so I got a hit. And I'm going to return this data value, 424242, whatever, back to my CPU. Okay? So far so good. Now suppose that instead I wanted to look up the address 4008. So what does that change in terms of what I want to access in my cache? It changes my index, right? And what would my index be in this case? You say that a little louder?
2.
2, exactly. Okay, so the only thing that it changes when I switch my address from 400C, which ends in 1100, to 4008, which ends in 1000, is that my index is now 2. Okay, so now if I go and I look at line 2 of my cache, the tag there is 0x58, and I compare that to my 0x40, and they're not equal, so this would lead to a cache miss. Okay? So a couple things to notice here is, number one, what that procedure is for figuring out whether we have a cache hit or miss. And the second thing to notice is that we don't actually store the entire 32 bits of our address in the tag field, because the index bits and the offset bits already give us some information about our address. So from there, we can already figure out what are the bottom, in this case, 8 bits of my address. And so that means that my tag just needs to store the rest of the bits of my address. So in this example, I only have a 24-bit size tag. Okay? All right. So now let's see if we can do even better. Okay? Well, we talked about spatial locality, and we saw that our, access patterns of memory, have both temporal and spatial locality. But why don't we try to, take even further advantage of our spatial locality, so that when I go and I fetch something from memory, you recall that fetching something from memory is quite slow. So it turns out that if I fetch multiple things from memory, especially if they're contiguous, in other words, they're right next to each other, then the incremental amount of time that I have to spend for fetching the other elements is much, much less significant than the startup cost, that I pay for getting that first element. And so, so what that means is, well, maybe it makes more sense for me when I actually have a miss and I go to main memory, why not bring more than just one word into my cache? Instead, I'll bring a bunch of words. Let's say in this example, I have 4 words, and I would fetch all of those, these are 4 consecutive locations in memory, and bring them into one line of my cache. Okay? So what are the advantages of this? The first is that if I'm accessing, address X, now I got a miss, I just brought address X plus 4 and X plus 8 and X plus 12 into my cache. So when I go and I try to access those locations, they're actually going to get a hit. Okay? The second benefit is that as far as how I'm making use of my memory, I'm now, storing a tag field for every 4 words of data instead of for every word of data. Okay, so I can use my cache memory more efficiently. The disadvantage, however, is that as I have more words per line, then, if my capacity of my cache is a fixed size, then the number of lines that I have is going to shrink. And so that might mean that, I might start to get more conflicts because I can't store as many different regions of memory in my cache at the same time. Okay, so how would this work? Again, I have the 2 bottom bits are 0 for the byte offset. Now my next 2 bits would select which word in my line I'm actually trying to access. So these we call the line offset bits. And because we have 4 words, we would have 2 bits for the line offset. And then the next set of bits are the index bits, which select which line in our cache we're trying to access. So again, here we have 4 lines, so we have 2 index bits. And finally, everything else is our cache. Okay? So, so basically, other than that, everything works the same as what we saw before, but now instead of, only being able to fetch one particular word from a cache line, we can actually select which word from the line we're actually trying to access. All right, so let's look a little bit at the trade-offs of block size, right? Like, how big do we want, of line size. How many words do we want to fetch at the same time from main memory? Do we just want to, keep growing it forever, or is there a point where we start to have diminishing returns? So if we look at the actual components that make up our average memory access time, we see that as we increase the number of words that we're fetching, our miss penalty, does go up because we're getting more things from memory. But as I mentioned, the startup cost of getting that first element, you only pay once. What about our miss ratio? Well, as we increase the number of words, what happens is that initially our miss ratio goes down because we take advantage of the spatial locality where we brought in things that were nearby, and now they're in my cache when I try to fetch them. However, if I make my line size too big, then I'm going to eventually be in the situation where I have too few lines, and now I'm going to get diminishing returns from my temporal locality, and as a result, my miss ratio is going to start to go up. And so if I put the two of these together, we find that there is, sort of this optimal size, which typically is around, 64 lines or so. And so when we use this line size, then we get the best performance from our cache, or something like that. And so that's what you'll typically see in modern processors. Okay, so what's the next thing that I have to worry about? The next thing that I have to worry about is writing to my cache. Okay, so I have a few possibilities of how I do my updates when I write to my cache. I can choose to, every time I write to my cache, to also immediately write the same value to my main memory so that my cache and my main memory stay in sync with each other. We call that a write-through policy. Another policy is I could just update my cache, and only when I take a line out of my cache, then I write it back to main memory. Okay, the advantage of that is I'm doing way fewer writes to main memory because I might write my line multiple times while it's in the cache. So why write it back to main memory every single time, right? And so, in fact, not only do I only need to redo it on replacement, but I can actually add an additional bit to each line, which we call the dirty bit, which says, did I actually modify this line? In other words, did I perform a write to it? And only lines that are modified actually need to be written back to main memory, because if I didn't modify it, then the values in that line are the same as what's in main memory. Okay, and so we add this dirty bit in order to minimize even further how often we need to write back to main memory. And finally, we have a third choice, which is not to write to the cache at all, and only write to main memory, and we call that a no cache write on write miss. As you can imagine, that basically means that it's never going to be brought into the cache. And typically, you're never going to use that by itself, but there might be cases where you want to use that together with another cache policy. But basically, the one that's the most commonly used is write back, because it makes the best utilization of our memory bandwidth. All right, so let's take a look at a couple examples of how we actually perform a cache write. So suppose that I have this example where I have a 16-line direct mapped cache. That means I have 4 index bits, and I have 4 words per line, so I have 2 line offset bits, and my write policy is write back. And let's say that I want to write the value 9 to this address 4818, okay? So this address looks like this, and I've color-coded it to show you the different fields. And so basically what we're saying is that I want word 2 out of the line that I'm going to fetch, and the index that I want is index 1. Okay? And so I've just elaborated that here. And so now let's take a look at index 1 and see, does this tag in index 1 match the tag that I'm looking for? In this particular example, it does. And so I get a cache hit. And now what I can do is I can just go ahead and update the appropriate word that I wanted to update. So I'm going to update word 2 in my line, which corresponds to this location right here. And so I change that to a 9. Notice that I also changed the dirty bit to 1 to indicate that I've now written to this cache line. Okay? So and what that dirty bit means is that upon replacement, I'm going to have to write this cache line back to memory. So now let's take a look at an example of a miss. Now what happens on a miss? So on a miss, if I look, at this example right here, I'm trying to access tag 48, but the tag that I'm currently, indexing is 0x280. So I get a tag mismatch, all right? So in this case, my tags don't match, so I have to go to main memory to fetch the thing that I'm looking for. But if I look at the dirty bit right now, it says 1. That means that at some point I actually wrote to this line in my cache, and so before I can get rid of it from my cache, I have to first write it back to main memory. Okay? And so I'm going to take this line and I'm going to figure out which addresses it corresponds to and write that back to main memory. If the D bit had been a 0, then I wouldn't have had to write anything back to main memory. And now once I've written it back to main memory, then that line becomes available for me to bring something else into. And so I bring my new line in with tag 48, and I load all the elements. Notice that I load the entire line, not just the particular word that I'm going to write to. Okay, this is very important because after the tag corresponds to the entire line. So if I'm only going to update the, one of the words, not the entire line, I must first read the entire line from my main memory and only then update the appropriate word. Okay, so first I read this line in, I cleared my dirty bit because now I have the same value as what's in main memory. And now I can go ahead and write to word 2 of this line, which will set this to 9 and my dirty bit to 1. Okay? Any questions about that? Great. Okay. I think just in the interest of time, I'm going to actually let this example be covered in recitation. And so let's move on to set-associative caches. Okay? So until now, we've been talking about direct mapped caches, for which, for any particular address, there was exactly one line that address could map to in my direct mapped cache. Well, you can imagine a scenario where at the same time, which is what that previous slide was showing, at the same time I'm trying to access two different addresses that happen to map to the same cache line, right? If I only have a space for one of those in my cache, then they're going to conflict with each other. And when I go to fetch one, the other one's not going to be there, and vice versa, right? So if, let's say, I have 2 data elements, one comes from location A, and another, let's say this is M of A, and another one comes from location B and has data M of B, and they both map to the same line, well, if I'm accessing A and then B and then A and then B, then I'm constantly going to be getting misses, right? However, if instead I chose to have 2 of these direct mapped caches operating in parallel, here I have a picture of 4 of them operating in parallel, then both my A and B can live in my cache at the same time. Okay? And so this reduces the number of conflict misses that we have in our cache. And so the way that set-associative caches work is that we have some nomenclature, which is that the number of rows that we have is equal to the number of sets. So here we've got 8 sets in this example, and the number of column is a number of ways. So this is a 4-way set-associative cache, so it has 4 columns. And so basically it means we've got 4 direct mapped caches essentially operating in parallel. So how would I go ahead and do a lookup in this cache? Well, most of the idea is still the same. I'm still going to have some index bits that are going to pick a particular row of my cache, okay? But now the index bits are not going to select just one cache line. Rather, they're going to select 4 different locations, all of which are in the same set. Okay? So what does this mean? This means that when something maps to a particular index, I can actually have up to 4 different addresses mapping to that same index living in my cache at the same time. Okay, and so when I go ahead and see whether my element is present, I now not only need to compare the tag for one of these caches, but rather I have to compare it for all 4 of them. Okay, and so when do I have a hit in this situation? I have a hit if any of the 4 matched the tag that I'm looking for. Okay, and you can imagine that there's, an end case of this where I have exactly 1 set, and we call this a fully associative cache. This means that basically any address can go into any line of my cache, but this becomes expensive because I now have to have the same number of comparators for my tags as I have as I have ways in my cache. Okay, so we're out of time. So in recitation tomorrow, there's just one last topic that I wanted to cover, which is how do we decide which element to replace, right? So we talked about 3 different types of caches. In the direct map cache, you don't have a choice. You only can map to a single cache line, so that's the one you have to replace if you need that location in the cache. But in a set-associative or fully associative, you have all of these yellow options to be replaced. And so we want to think about, well, what's going to give us the best performance in terms of how do we decide which one of these existing cache lines should be the one removed from the cache. Okay, and so we'll stop there and we'll go over that in recitation tomorrow. One last thing, we have these cool RISC-V inside stickers, which are a modification to the old 6004 beta inside stickers. When you go to get your Lab 6 checkoff, make sure you get one of these and attach it proudly to your laptops. This has been a long-running 6004 tradition, and you should be following it and continuing it. All right, thanks everybody.